case, it's characterized by fever, the same rash, bony overgrowth of the epiphyses of the long bone, and central nervous system disease. So in any case, Hal Hoffman at the UCSD mapped the gene for both familial cold autoinflammatory syndrome and Muckle-Wells to the long arm of chromosome 1. And in his candidate region, it turned out that there was a putative gene that had a pyrin domain. So he sequenced that gene, and it turned out that there are mutations in that gene that are associated with disease. Moreover, this protein encoded by it actually binds ASC, the same protein that pyrin binds, and has a role in regulating IL-1 activation that we'll talk about in a little bit. So anyway, our involvement in this happened when we were referred a patient, and this was actually Raffaella Goldbach-Mansky, my colleague, who was referred a patient supposedly with systemic onset JIA, idiopathic arthritis, from North Carolina. And he's shown right here. Now, there were some features of his illness that didn't quite fit with systemic onset JIA. Like, for example, he had this rash, which was sort of urticarial in appearance. He had papilledema. He had some ventricular megaly in his and he had these funny, knobby-looking knees. This is not what you see in systemic onset JIA. Raffaella was quite astute and, in fact, determined that this patient had NOMID, neonatal onset inflammatory disease, which at that time was not even thought to be a genetic disease because it's so severe that most patients who have it never grow up to have kids, or never have kids when they do grow up, and so it's thought, or it was thought, to be a sporadic disease. Well, in any case, I had happened to have seen at that same week, during that same week, a patient with Muckle-Wells. And so we had two astute fellows, Moose Moa and Mirka Novak, who saw Raffaella's patient and saw my patient on the service, on the rheumatology service. And they said, well, these patients must have something that's related to one another because the rash looks very similar. So in any case, we didn't think that there was anything to that. I sort of poo-pooed it, but we figured, well, what? Were mutation negative, but we then went back and looked at them to see whether some of them might have mutations. So here's a child from Puerto Rico, and you can see that he does have bony lesions that look more like NOMID. Here's the pedigree. We tried to sequence the IL-1 receptor antagonist gene in his case, and Ivona was not able to amplify the DNA, although she could amplify other genes. So we started thinking about, well, could there be some sort of a genomic deletion? And in point of fact, when we did a SNP chip on this patient, there is a 175 kb deletion on chromosome 2 that includes the IL-1 receptor antagonist gene, but also 5 other genes that are in the IL-1 family that are missing in this patient. It leads to a more severe phenotype than the classical, if you want to call it classical, NOMID. So in any case, so yet another example of this. So just in terms of population dynamics of this, I've told you about Newfoundland, and we screened some population samples there, and we found a couple of carriers out of that. All of the Dutch patients, the Dutch ancestry patients, come from the Bible Belt of the Netherlands, something I'd never heard of before we started doing this book, but it turns out there is one. And then actually the Puerto Rican patient comes from the northwestern part of Puerto Rico, the Arecibo region. And via Bilbao, we were actually able to get some samples of healthy individuals from that area of Puerto Rico. And it turns out that 3 out of 119 samples were positive for this 175 kb deletion, which would predict a frequency of about 1 in 6,000 live births in this area of Puerto Rico. So it is interesting. In any case, just to sum up this part of the talk, so if you compare NOMID with DIRA, they're both caused by mutations in genes in the IL-1 pathway. And you can see that there are differences, marked differences in the phenotype with regard to rash, the bone involvement, and presence or absence of CNS involvement. And this reflects perhaps, at least to some extent, where the lesion is in the pathway. In the case of NOMID, it's at the level of the inflammasome. In the case of DIRA, it's at the level of the regulation of IL-1. So in any case, there are then a number of diseases that are diseases of IL-1 signaling that we've talked about, and some that we haven't talked about and that we won't have time to. So in any case, we have Muckle-Wells syndrome and FCAS, that's mutations of cryopyrin, also known as NLRP3, shown here in this inflammasome. You have FMS that's caused by mutations in pyrin that also has a role in regulating IL-1 activation. And then hyper-IgD syndrome, which we didn't talk about, is mutations in another protein that post-translationally modifies some of the signaling cascades that activates this pathway. A different rash still. Then we have DIRA, which is a mutation in a negative regulator of IL-1 signaling. We have Papa syndrome, which we don't have time to talk about, but is caused by mutations in PSTPIC1, a protein that binds pyrin and has a role in the activation of the IL-1 pathway. This is pyoderma gangrenosum in a patient of ours from Kansas City with this disease. And then reproductive diseases even can be associated with this. This is recurrent hydatidiform mole, caused by, at least in some cases, mutations in NLRP7, a cryopyrin lookalike. So in any case, just going a little bit more broadly, then we have a number of diseases besides those mediated by IL-1 that are these autoinflammatory diseases. I won't, for the sake of time, go through the whole list, except to point out to you that even diseases like gout, a crystal deposition disease, is now recognized to have a major pathophysiology associated with IL-1 activation, and in fact, IL-1 inhibitors are being looked at in clinical trials for the treatment of gout. This is just a slide indicating that there is a spectrum of autoinflammatory diseases, basically going from monogenic ones to polygenic ones, and then on the other end of the spectrum are the classic autoimmune diseases, which then got us interested in the possibility of polygenic autoinflammatory diseases. So I'll finish this in 3 minutes. Let's see if we can finish this in 3 minutes. So anyway, we had been interested in the genetics of polygenic autoimmune diseases through our involvement in something called NARAC, the North American Rheumatoid Arthritis Consortium, which I had been involved in since 1997 with Peter Gregerson at North Shore Hospital. And in 2007, Wayne Remmers and our group had identified variants of STAT4 that are associated with both susceptibility to lupus and RA. So we had some interest in polygenic diseases, and so we took as a target Behçet's disease. Now, Behçet's disease is another disease that's common in the Middle East. Behçet's disease is characterized by a triad of oral ulcerations, shown here, eye inflammation, and this is what's called hypopyon. This is actually pus in the anterior chamber of the eye, and genital lesions. It does run in families, and so we did think that there was a genetic component to it. So we established a collaboration with Ahmet Poor in Istanbul, the lambda S of greater than 10. So that's telling us that there is a healthy genetic component to this disease. So we looked at 1,300 roughly unrelated cases from Turkey and 1,300 geographically matched controls. We looked with the Illumina 370K SNP chip for associations, and after quality control, we had about 311,000. Some of these are copies of So in any case, this is the Manhattan plot from those studies. This is new information. We haven't even submitted it for publication, so we're all sworn to secrecy. But in any case, there is a major HLA component, as there is for a number of these diseases, and HLA-BW51 is the HLA locus that's associated with Behçet's disease, although